Now that we talked about ordered pairs and maps, now let's define a relation. As before, again takes two sets, A and B, and you have some elements 1, 2, 5, 7, 9. Let's say this is 3, 4, 10. And now what you want to do is that you just want to find a map that takes the elements of set A to two elements of set B. Again, you can just, let's say I'm drawing the arrows like this. So this is again some sort of a mapping, right? And you can construct ordered pairs from it. So this is what we call a relation. The mapping itself is a relation, this mapping F. So this is our relation. We don't know what the relation is. We just know that this is some sort of a relation. At this point, we don't bother about it. And we can construct ordered pairs from it. We can plot it. We will talk about plotting when we talk about graphs and plots of functions and relations and stuff. So the relation is nothing but the mapping itself. So this is another fancy way of saying this is a relation. Okay. However, we do see the fact that to form a relation, you need to take into account all the elements of the input set. And now we will define a function. What is a function? Function is a very special kind of mapping or a very special kind of relation. So for a function, let's say you have a relation like this guy over here. So let's say you have some relation from set A to B, and you want to know whether it's a function or not, whether it's a function or not. So first, what you have to do, you have to define a function, right? Because without defining, you can't do anything in mathematics. So we define the function in the following way. Let's say we have a input set A and an output set B. So this is my input, this is my output, and the relation between them is f. We will call f a function if for every element in A there are no multiple outputs. If for every element in set A there is only a unique output into set B. What this means is that, let's say you have three elements in set A. For these three elements, all the outputs in set B cannot be the same. Even if you had two elements in set A, and if they produce the same output in set B, that would not be a function. And we'll clear this. We'll clear this with a few examples. Like word-wise, this seems a bit complicated right now, but when we see examples, this will all be clear. So let's just dive into an example, a very simple example. Let's say we have a relation from set A to set B. Set A has 1, 2, 3, 4. It has 5, 6, 7, 8. So let's say 1 goes to 6, 2 goes to 5, 3 goes to 7, 4 goes to 8. The question is this relation a function? We see that for every unique input, we are getting unique outputs, right? Unique inputs corresponds to unique outputs. And according to our definition, for every unique input, the outputs needs to be different. So in this sense, this is a, or this relation is a function. Okay, that's good. This was not that complicated at all. So now let's look at another example. Let's say I have 1, 2, 3, and I have an output set as 1, -1, and then I have, let's say, 4. All right. So let's say for 1 you have 1, for 2 you have -1, and then if you again input 2, it can either be -1 or 4. And for 3, let's do another one like this. 3 goes to 6. Is this relation a function? The answer is no. It is not a function. This punchline that we talked about gives rise to a graphical method called the vertical line test. We will talk about this when we talk about plots and graphs. So this will give rise to identify functions through something called a vertical line test. So this is the very basics of functions and relations, and we will talk about algebraic functions next. So that's the next topic. Algebraic functions. Well, they're mostly functions, and some of them are just relations. So let's call functions slash relations. So let's say we have a relation between y and x, where y is our output and x is our input. And the relation in between, or the function between them, is f, such that it takes some input x and spits out y. People usually write it like this: y equals to f of x. And a very common example is the example of a straight line. So let's start with that. Let's say y equals to x. Let's say. So what does this mean? And again, since this is pre-calculus, all of our discussions are constrained to real number sets only. So whenever we talk about inputs and outputs, we will only consider real numbers. We will not consider complex number quaternions and stuff like that. So let's say I take the value of x 1, and if I put it over here, plug into this relation, the value of y is still 1. When the value of x is 2, value of y is 2. Value of x is -100, value of y is -100, and so on. Now the question is, obviously this is a relation because for every input you can get an output and you can consider or construct ordered pairs and stuff like that. However, is this a function? The answer is yes, because for every single input you get a unique output, and one single input doesn't correspond to multiple outputs. So that's why it's a function. Now, if you consider another relation, let's say y equals to x squared, let's say. Now, if you take x equals to 2, y becomes 4. If you take x equals to -2, y also becomes 4. If you take x equals to plus minus, okay, let's not write plus minus, let's say plus 10, y becomes 100. If you take x equals to -10, y also becomes 100. So if you put numbers like this, you'll realize that if you to take inputs, you will see for every input you can get outputs. So that qualifies this as a relation. And you can see that for a single input, there are no multiple outputs. However, for different inputs, you can get the same output. So does this qualify this relation as a function? The answer is yes, because the criteria of a relation being a function was that for a single input, there cannot be multiple outputs. However, for multiple inputs, sometimes you can have a single output. Okay, let's consider another example, and this will make things more clear as well. Let's say y equals to 5. Now you might say, where is my x? Well, x is just not there. Y equals to 5. So no matter which value of x you take, because x does not exist on the right hand side, y is always equals to 5. And this is an example of a constant function. So whenever you have some inputs over here, however, all these inputs gets mapped into only one number, this sort of a relation is a function, first of all, and this function is called a constant function. And one thing I forgot to mention a little bit earlier is that when you write y equals to f of x, we read this as y is a function. Since we'll deal with functions in calculus, and obviously you'll also deal with relations as well. But what happens is that people really don't distinguish between relations and function at that point. Function is just a name that people give to things like that look like this. So with that in mind, from now on, we'll just call all of them as functions. So we call it y is a function of x. And this really means that x is your independent variable. That means you are at freedom to choose whatever value you take. Depending on what the value you take, there will be some function or some mapping f that will take that value in and produce some y. So you can choose freely for the values of x. However, when you choose a specific value of x, the value of y is determined by the nature of the relation or the function f. That's what it means. So this is independent. People usually call it independent variable. And this as the dependent variable. One can also write a what one can do is that one can also write a function like this. Y is a function of x. And in this case, y is your independent variable and x is your dependent variable. So it really depends on the context of the problem, which is your independent variable and which is your dependent variable. But for now, if you are way too confused, I suggest you stick with this notation where x is your independent variable and y is your dependent variable. But as we move on towards calculus, you will see that it will totally depend on the problem that you're dealing with. So you'll have to construct your functions or you'll have to construct your relations according to that. All right. So let's now that we have some ideas on what functions are, let's take a look at few more examples. Let's say I have a function like this, f of x equals to x plus 2. And I ask you to find the value of f of 10. What is the value of f of 10? What this really means is that you take the value of x equals to 10 and you plug this back into this equation where f of x is written as x plus 2 and you just do the algebra to find the value. So in this case, f of 10 is just 10 plus 2, which is equals to 12. That's all you have to do. So if you see f of 10, you just put x equals to 10 in your function expression over here on the right side. Similarly, if you have f of x, let's say some quadratic function, ax squared plus bx plus c, where a, b, and c belongs to the reals or the real numbers, and I ask you to find what is f of k, where k is some real number as well. You just write f of k is just ak squared plus bk plus c. That's it. That's all you have to do. Now, I can make you do some algebras as well. Let's say f of x is equals to x minus 2 divided by x plus 3. I ask you find the value of x or x1, let's say, such that f of x1 is equals to 1. How do you do this? Again, this is very simple. The condition given to you is that f of x1 is equals to 1. So instead of x, you just put x of 1. You write the whole thing. You do the algebra. X minus 2 is equals to x1 plus 3. As you can see, this will give you minus 2 equals to 3, which is not possible because negative 2 is not equals to negative 3. So then you can write there is no such x1 such that f of x1 is equals to 1. And that's it. Okay? You can do a lot of algebra like this. So this gives us some idea on how to deal with functions. Now you can look into any pre-calculus exercise books to, to do some exercises like this so that you can, get used to this notations and stuff. So what we're gonna do is that we're gonna talk about some function compositions next. And from there, after we do function compositions, we'll move on to the topic of domain and range.